You're on.
All right. Okay, so we just finished talking about wavelength and frequency and the components that make up a wave, and now we're going to talk about two particular types of wave. One is the transverse wave, and the other is the longitudinal wave. Okay, so let's first define them. Okay, a transverse wave, my little board says, is a wave whose propagation, its movement, is perpendicular to its oscillation. Now, the oscillation is the movement of the medium. Okay, so here's an example of a transverse wave. The medium moves up and down. However, the wave, as it propagates, it moves in a direction that is perpendicular. So if you look at, I'll grab my pens back here. If you look at the oscillation, right, my oscillation in my transverse wave is moving up and down like this, right? However, my movement of the wave is this way. So you can see that when the movement is perpendicular, it moves this way, my wave oscillates this way. That's what we call a transverse wave, okay? A really good example of this, have you ever done workouts with the rope, right? The big long weighted rope that you can pull up and down like this. That's a fantastic example of a transverse wave because you pull up and down like this, but what happens to the movement of the wave you're creating? You're making the disturbance, now the wave is moving, but the wave is going to move this way along the rope. It's going to move in a direction that is perpendicular to your actual oscillation of the medium, okay? Water is the same way. Water actually moves up and down, which makes sense if you're in water. You can think about it. When you have movement in water, the water moves up and down. However, when a wave is created in the water, the wave is going to move perpendicularly or transverse to the movement of your medium. Okay, so a weighted workout rope would be a transverse wave. Water would constitute a transverse wave, and then light is also defined, or it is categorized as a transverse wave. Okay, so when you're talking about light, you're talking about a wave that's going to move perpendicular to the oscillation of the medium. Okay, the other kind of wave that we're going to talk a lot about is a longitudinal wave. Now, a longitudinal wave is a wave whose propagation or its movement is parallel to its oscillation. Okay, so if you can see here, I've got the movement, the medium moving this way, right? So its movement is really in this direction, right? This is the movement of the medium. And then the movement of the wave goes in the same direction. So it's like this. So these two movements are parallel to each other. So that is what we call a longitudinal wave. And a slinky would be a good example of that. A slinky moves back and forth like this, right? When you create a disturbance, the movement of the wave is going to happen in the same direction as the movement of the medium, okay? And sound would also be what we consider a longitudinal wave. Now, we're going to talk for just a minute about the nature of sound, the physical nature of sound, okay? So, if we have this would be our membrane here, okay? All right. So a sound wave occurs when air is pushed outward from a source. And as it's pushed, there's a compression that occurs. And when the pushing ceases, what we call something that is called a rarefaction actually occurs. And if this happens at a regular interval, then this series of compressions, which are the crest, okay, so if you're drawing the wave, this would be this compression here would be the crest, and this where I've noted the two different things by two different colors. So my compressions are in black here, and my rarefactions are in pink. Okay, so this black would be my crest, and down here would be my trough, and up here would be my trough. Up here would be my crest, down here would be my trough, etc. I don't have a lot of room here. But that's the idea of how that sound wave actually plays out when we look at the physical nature of the sound wave itself, okay? And obviously, when it looks like kind of like this. Here's my little man, Ethan Grimes. Took a lot of time to draw this little man, so you should be impressed by my lack of drawing skills here. Yeah, right? And so these little things would be the movement of the sound as it moves out from the little guy's mouth, okay? Now let's shift gears for a second and talk about how we hear sound. It happens actually in a similar fashion. However, instead of obviously we being the producer of this particular wave, our tympanic membrane, our eardrum, is the receptor of the longitudinal wave. So it's going to receive the compressions, and then the rarefactions will happen when the compressions cease. And so then it takes those vibrations that are happening on our tympanic membrane, and it basically they're passed into our organ of hearing, where they are converted into basically nerve impulses, which then are transmitted to the brain for interpretation. So that's kind of how we actually hear those sound waves that are traveling through the air. Okay, let's see here. All right, so real quick, I'm going to erase and do one more set of equations, but before I get to that, we're going to talk about two components to the longitudinal wave that impact how we hear sound. Okay, the two things that impact how we hear sound are frequency and amplitude. And obviously we know that frequency has to do with the length of the wave itself, right? It's the same equation, right? The frequency equals the velocity over the wavelength. And I think in the last video I may have said frequency when I meant wavelength. But anyway, so we have frequency and amplitude. The frequency has to do with the wavelength, okay? And that has to do with the pitch, or if you're thinking about sounds in terms of notes, that's how every frequency, okay, so every frequency that you hear, which really has to do with how high or how low a sound is, has to do with the actual wavelength of that. And then the other component of this wave that impacts how we hear is amplitude. And again, if you're looking at our sine wave, I'm going to make this be my wave. I'm just going to draw a line through it that represents equilibrium. Okay, there's my longitudinal wave. It's not perfectly drawn, but you're getting the idea. So the frequency has to do with the pitch, how high or how low it sounds, has to do with our wavelength, which is inversely related to frequency, right? And then if we measure the distance up or down from equilibrium, which we know is our amplitude, that has to do with how loud the sound is, right? So if it's got a very large amplitude, then we have a loud sound. If it's got a high frequency, if the frequency is large, meaning the wavelength is small, that would correspond to a high pitch, okay? And a large amplitude corresponds to a loud volume, okay? Now, three things for us to remember about sound waves in general. Sound waves are longitudinal. The frequency is a primary factor in determining pitch, so the high or how high or how low a sound is to our ears, and then amplitude determines its volume. So I'm going to do one more erasing, and we'll do one more section on Doppler effect and also how we determine the frequency that we actually observe something versus its actual frequency. And if you've read the material, you know that the frequency will seem to change depending on whether an object is moving towards you or away from you. So we'll talk about that in just a minute.